From Photonics Media, this is the podcast that takes listeners inside the physical science of light as we explore groundbreaking and industry-shaping progress in lasers, optics, imaging, metrology, and sensing. Each episode, our hosts welcome optics and photonics luminaries, rising stars, and market leaders for robust discussion about the trends shaping the field of photonics. From research and development to commercial innovation, we're on the air for unparalleled insight, offered on All Things Photonics. All Things Photonics is brought to you by PolyScience and Lumencor.
Today's episode is brought to you by PolyScience. For over 60 years, the PolyScience line of award-winning temperature control equipment has been helping the photonics industry reach its goals safely and efficiently. Our products are made in America and delivered globally. Please visit polyscience.com to learn how we can help you. Changing the world of chillers is more than a tagline. It's part of our history. Today's episode is also brought to you by Lumencor. Lumencor excels in the manufacture of technical lighting, scanners and imagers, and metrology. Visit us at lumencor.com to see how we can best support your new products and OEM production.
Paul Prucnal's forecast for the near and more distant future of neuromorphic photonics manages at once to encapsulate a technological promise as well as a conservative essence. The risks of overstating or worse, overpromising on the capabilities of this still nascent area of photonics far outweigh the hype that Prucnal could no doubt stir by detailing the potential for neuromorphic photonics if he opted to do so in a more frenzied way. Today on All Things Photonics, we give our listeners a chance to hear from Prucnal directly on this very topic. The acclaimed Princeton professor joins colleague and fellow neuromorphic photonics champion Bhavin Shastri from Queen's University in Kingston, Ontario, to discuss neuromorphic photonics. From defining this high-potential, high-technology realm of photonics to breaking down its roadmap, our experts aim to flesh out one of the area's most sophisticated sectors. Two themes guide our conversation today. First, and as mentioned, we dive into the reality that much of the conversation and intrigue around neuromorphic photonics today considers applications that lack a well-weathered roadmap. This suggests that neuromorphic photonics cannot be wholly detailed without exploration of technology that has yet to find widespread real-world development. This, Prucnal and Shastri say, contributes greatly to a conservative technological forecast. We also discuss something that ought to sound familiar to those acquainted with silicon photonics: the lack of a so-called killer application. In addition to discussing what may possibly emerge as a killer app for neuromorphic photonics, today's guests also offer their wisdom on what must happen for neuromorphic photonics to find a, quote, killer application. It may not be an entirely fair question, and it may not be the proper question to ask to gauge the progress of the field looking ahead. Nevertheless, in our discussion on this ascending technology, our goal is to get to the bottom of how a promising technology could rise to the top.
So, while I have you both here, two foremost authority figures on the topic, I'm going to start small in a sense and just get this out of the way first. And I'll focus it to you, Paul. What is neuromorphic photonics?
Well, I would say that neuromorphic photonics is a technology that tries to exploit the performance advantages of photonics to implement signal processing and computing functions while taking its inspiration from neural processing in the brain.
And a lot of the conversation and the intrigue around neuromorphic photonics today considers, I think, applications and technologies that lack what we might call a well-weathered, wholly established roadmap. And that isn't meant to knock the technical maturity of optical communications or silicon photonics or anything like that, because they've achieved quite a bit of that in recent years. But it does suggest that our conversation on neuromorphic photonics is going to cover technology that hasn't quite yet found widespread real-world deployment. That's my preamble. But before we go in this direction, I just want to ask, what advances, or more broadly, in what technology areas have the most fundamental advances taken place to allow us to discuss neuromorphic photonics today?
So I would say, so maybe to answer this, I know we're going to talk a lot about neuromorphic photonics and applications today, but I guess maybe just a bit more historical perspective, right? So when the laser was invented, people started thinking about computing with light around that time, and in fact, people started talking about neural networks also at that time. So the work really kind of picked up, using optics for highly parallel signal processing and linear vector matrix multiplication, and this was shown by Joe Goodman back in the 1970s. But in a neural network, a neuron also needs to do some type of decision making. It needs to do a sort of a yes/no type of it needs to have a yes/no type of output, and this is a highly nonlinear function. And so what neurons really require is what is called a nonlinear activation function. So the impetus to bridge this gap between the photonic device physics and neural networks came from our realization that photonics can not only be used to implement interconnects needed in neural networks, but also the physics of photonics can be used for implementing nonlinear decision functions as well. And I think this was kind of the missing link for many, many years, right? To have both this the linear part and the nonlinear part of the neurons both implemented on a single device. And I think this is what kind of ignited sort of the interest in now what we call neuromorphic photonics.
And I just want to get off script for a second, because neuromorphic photonics is its own distinct branch of photonics, but it envelops considerations that other disciplines in photonics really don't. It's a very focused area of this greater field. And I'll ask both of you, but I'll start with you, Bhavin. What is the background that drove you to neuromorphic photonics? Did you come at it through a strictly photonics lens, or an electrical engineering lens, or a physics lens, something else?
It's a very interesting question, and I guess okay. So in my case, I guess this, you can approach this from many ways, but I guess sort of personally, I was actually, as an undergraduate student, I was in electrical engineering, and as an undergraduate student, I was one of my summer thesis project, which led to my undergraduate thesis, was on machine learning. And then I got interested in, I took a course on electromagnetic waves and optics, and I got interested in lasers. And then I kind of made a switch to go into photonics. And while doing my PhD, when I was coming towards the end of it, I went to this conference. This is in Mexico. I think it was the Summer Topicals, and I saw Professor Paul Prucnal's talk there on the photonic.
I've never heard of him. Is he well known? No,
Sorry.
He's another member of academia. Yeah. Sorry, go on.
Yeah. No, so I guess
that's where we first met.
Yeah, that's where we first met. So I heard a talk on a photonic neuron at that time, and immediately in my head was like, I did my undergraduate in machine learning. I have done my PhD in optics and photonics, and here is Professor Paul Prucnal from Princeton talking about a photonic neuron. It kind of just combined both the fields at the same time, and for me that was really that type of aha moment. And so I immediately ran up to Paul right after the talk, and that was it. That was a life-changing. Yeah, exactly. Yeah. So I kind of approach it more from electrical engineering and then applied physics, and yeah. So.
And now, what about you, Paul? Because Bhavin found Paul, but I suppose how did Paul find Paul?
Well, I think my story goes back several decades earlier than Bhavin. It's probably a lot longer story that I'll try to keep short. But I guess I would say that everything that I've done that has been successful or worthwhile or meaningful, and I say this in all sincerity, I owe to my PhD advisor, Professor Mal Teisch, the book Saleh and Teisch, Fundamentals of Photonics. And Teisch, when I studied with him for my PhD at Columbia, was an optical physicist at that time. He still is, but he was interested in visual psychophysics, which is a field where they were understanding how information is processed in the brain, spike processing in the brain, photons coming in, spikes going out, how to understand the statistics of all that. And Teich developed a collaboration with Bill McGill, who happened to be president of Columbia at that time, and himself was a mathematical psychologist. So I started working with them at that time, and that was in the 1970s. And I did my my PhD on optical communications, but also visual psychophysics. And ever since then, I was interested in the bridge between optical physics and information processing in the brain. And again, that goes back 5 decades to the 1970s and early 1980s.
You and I, Paul, met at the Opto Conference plenary at Photonics West earlier this year. And the plenary for the Opto Conference was such that your session came immediately after that of Roll Bates, who considered a roadmap for silicon photonics in this present age of photonic and optics integration. How do you classify the coexistence or the cohabitation that neuromorphic photonics and silicon share on this broader integrated photonics roadmap?
Yes, that was really an excellent talk. I learned a lot from it. I think Professor Bates was right that there's an enormous market on the roadmap for silicon photonics in small form factor pluggable transceivers in data centers where they need hundreds of thousands or millions of those. He talked also about there being an emerging market for silicon photonics in biosensing as well. We have a much more of a new technology that's coming out. But I think that in the near term, and I think Bhavin would agree with me, that neuromorphic photonics will find its way into that value chain of integrated photonics by addressing what I would say is the bottleneck at the edge of cyber physical systems. Physical data coming in, processing at the edge. That's where I think that analog photonic signal processing can have a distinct advantage over electronic DSP, digital signal processing. So one example is that in the near term, neuromorphic photonics might be used to reduce interference in the wireless spectrum. It's becoming increasingly crowded, and do that in real time analog processing of radio signals, for example. That's hard to do if you have to take broadband signals and use digital signal processing, use A to D converters, for example. Another example is directly solving differential equations from input signals to achieve low latency control, for example, in robotic applications, very fast control, low latency there. Bhavin, you probably have some things to add to this list.
Yeah, so I think to complement about low latency, right? It's so there are a lot of these applications where the real-time capability is very, very important. I think just to complement what Paul has already mentioned about applications, another area that I find very, very interesting that I think where neuromorphic photonics can potentially play a role, or in general, information processing and photonics is in solving large-scale combinatorial optimization problems. And in this kind of problems, it's not only about finding a solution fast, but it's also about to ensure the scalability with the problem size. So as the dimensions of this problem grows, right, typically what you find on other computing platforms is the time to convergence to reach some solution, it increases exponentially with the number of dimensions that you have. But with photonics now, what you can do is that you can exploit multiple degrees of freedom, of light. You can exploit the wavelength. You can exploit you can exploit mode. You can exploit the polarization of light. And the point is that by exploiting this multiple degrees of freedom, the scaling of this problem becomes a lot more manageable. And so I think these are the areas where I believe that that photonics can play a significant role.
And I think this segues nicely into that last response, but I want to talk about present barriers and bottlenecks to broader adoption, either as a direct application or for functions like signal processing or compute. What is hampering the adoption of neuromorphic photonics right now?
Bhavin, can I start? And
please, yes.
Right. So, well, I think the most significant barrier to the broad application of neuromorphic photonics is, in fact, mistakenly viewing it as a solution to every problem. That's a recipe for failure. It's very hard to compete with the performance of digital electronics. That already excels at digital signal processing in terms of size, weight, and power, and very hard to compete with electronics and computing. It's also a moving target. So we have tried to be very careful to focus on applications where digital electronics cannot currently reach, rather than compete. So that could be, as I think I've mentioned, real-time broadband signal processing applications. Now, having said that, there are challenges that have to be overcome in the technology. And Bhavin, maybe you want to address those.
Yeah, so I think, I mean, to achieve this type of practical implementations, right? One does not only require, this, of course, we require this large scale integration of multiple components on a single chip. And this is really being enabled by silicon photonics, right? As was also mentioned a bit earlier. But with silicon photonics, right, it's very good for guiding light. It's very good for modulating light. But you need other things. You need to be able to, we talked a bit earlier about providing nonlinearities to do this type of decision making. We need to, for example, we need to have light sources. And so the other big challenge is not only about having or piggybacking on silicon photonics, which is enabled by this, the last few decades of investment in CMOS fabrication, but it's also now the challenge becomes now integrating different types of materials on silicon photonics, which can then provide other types of functionalities. For example, right now there's big push towards what's called compound semiconductor on insulator, right? We want to be able to integrate things like thin film lithium niobate. We want to be able to integrate 2D materials like graphene. We want to be able to integrate polymers. Each one of this is has its own specific purposes, and I think this is one of the big barriers, for demonstrating large-scale systems with the right functionality. Is getting all these materials all integrated on the silicon photonics platform, right? Which is not really offered by any foundries right now. I think the other challenge is the integration of CMOS and electronics. So this is really needed, but there are just different ways of doing this. There are different. You can do monolithic integration. You can do flip chip bonding. There are pros and cons of each, and again, there's not one well-defined method, at least in my opinion. Finally, there are things like packaging and also the reliability of the design and the manufacturing, right? So unlike electronics, where you have this really sophisticated design tools, that doesn't really exist for photonics. And I think that those are all the challenges that I feel in that vertical stack that need to be solved to get to large scale systems, and then look at the applications that it can potentially enable.
So it's an interesting dynamic, because on the one hand, you're staring down technology with considerable potential, but also one where you have to be mindful that the roadmap is best looked at somewhat conservatively. I just want to ask about that dynamic before we jump into AI, which is my next line of questioning. How do you approach a conversation with someone who may understand, one of either the roadblocks, the bottlenecks, the limitations, or who may only understand the vast potential? How do you keep that equation grounded in reality?
Paul, do you want to go for this one, or?
Oh, go ahead, Bob. You can start.
So it's a very interesting question, and I think they kind of feed onto each other, right? It's like at times you want to be able to show an application that drives the technology. At times you want to show the technology that drives an application.
That's right. Yeah.
And so in some cases, I think a very good example here is with silicon photonics, that what really drove the technology was the telecom industry, right? It's you needed better modulators, faster modulators, efficient modulators, and so that in turn drove the people to invest in silicon photonics, and that problem, I would say maybe it's largely solved, but I have to be a bit careful there. But then, so we are kind of back into that into that era, right, where we feel that there needs to be a push towards accelerating the technology, by keeping the eye on what applications there would be. But then, sort of the business side is more about, I think that's sort of the science side, right? It's more about like we want to develop this so we can enable this. The business model is, or the commercial side is more towards like sort of the opposite. We need, hey, this is the application we need to solve, and therefore let's push the technology forward. And so I think we are at a time where there's this very delicate balance, and so maybe it's a bit earlier to answer this question, but I think we're kind of just at that fine balance right now. So I don't have a specific answer, but I think I think not only neuromorphic photonics, right? But I think quantum photonics, I think programmable photonics, I think signal processing, biophotonics, neurophotonics. I think these are so many different areas that are kind of trying to push that envelope, right? And I think it's not going to just be one of these fields of photonics, but I think it's going to be a combination of all these fields that's actually going to drive the mass adoption of integrating all these materials and better design tools and everything. Yeah.
I'll bring in AI to the conversation now, because you can really talk about any sector, and the influence of AI, and an interesting response is going to be forthcoming. But I wanted to frame the question in the context of the neuromorphic photonics roadmap. It is a continuation of that question: what has AI done for the roadmap? I guess I want to ask about opportunities. Where can AI contribute to advancing neuromorphic photonics?
Paul, would you like to take this one, or?
No, go ahead. It sounds like you have something to say.
Well, I think so first of all, artificial intelligence, it's not that it has not just arrived, right? It has been there since the 50s. Now, of course, one of the main reasons AI gained a lot of prominence in the last decade was due to the huge increase in performance of electronic chips, right? We started making better graphical processing units, and now tensor processing units, and now specialized ASICs and things like that. But it's also the availability of these large data sets on the internet, which did not exist before. So these two things kind of came together, and that's what kind of drove the implementation of this algorithms that needed a lot of data and that needed faster hardware. Now, our work on the photonic neurons started with the goal of building fast neural networks for analog computing and cyber-physical systems applications, as Paul mentioned earlier. So I would say that though the popularity of AI has helped with the visibility of neuromorphic photonics, it hasn't really changed our roadmap much. So digital computers are already very good at AI. And so what our hope is that our technology platform will be used as co-processors or special purpose devices for AI. We're trying to, as Paul mentioned earlier, we're trying to look at applications that could fundamentally be enabled by our technology. We're not really trying to compete with what's already out there. Yeah.
Is there an element of this combination, this potential combination of neuromorphic capability and AI benefiting society? I mean, is there potential there, and do you view that with a degree of excitement?
I do. I would. Paul, would you?
Well,
yeah.
Well, of course. I mean, I think the subject of whether AI is benefiting society and what its potential is a wide open question right now. And to the extent that photonics as applied to AI might accelerate that technology in some way, I think the same question exists. I think personally, I'm viewing this, as I said, as as something that's a co-processor that is enhancing the performance of signal processing systems, that's enhancing the performance of robotic and control systems. And so, it will be benefiting society in ways that it's going to be helping to advance other technologies.
Are those technologies principally in the field of photonics or on the periphery of photonics, or are they, up and down the value chain of technology all over the place?
I think they're up and down the value chain all over the place. But I do think in places where you can put chips that will help you right where the information comes into the system to do fast processing. And again, I spoke earlier about RF and wireless systems. And those are places where we have a wireless spectrum. It's very limited in its bandwidth. There's more and more demand for it. And it's really impossible to process all the information coming in simultaneously. If you want to find holes in the radio spectrum, if you want to find threats in the radio spectrum, and to do all this in real time. So this is an example where, for better or for worse, one can put something at the front end of radios, whether they be cell phones or they be communication systems in the defense sector, that can potentially handle these signals in real time.
The progression of a technology is it's infrequent that it's linear, that it follows sort of this path that you were able to anticipate and project. But the evolution of neuromorphic photonics, since you, Paul, co-authored the seminal book on the topic now 7 years ago, I guess I'll rephrase this question because I'm speaking with the person who literally wrote the book on the topic. You issued some degree of a forecast. Has it been what you expected when you wrote that book 7 years ago?
Well, so I've been around the block a few times on a few technologies, and for better or for worse, kind of maybe it's cynicism, know what we might expect as a new idea comes out. And so, we started on this way back in 2009. We didn't write the book until 2017. But when we wrote the book, and it was myself and Bhavin and my graduate students, we had real concerns. I had real concerns that once people understood the potential of this field, that there might be some who would jump in right away and make unrealistic claims and promises. You probably know what I mean by that. And that can quickly discredit a field. We've seen that happen in other similar fields in the 1980s and 90s. So I'm very happy that numerous groups have jumped in, particularly, I think, our colleagues in Europe and, of course, our colleagues in Canada. And they're making conservative claims, and they're making seminal contributions. They're not overselling, they're not overblowing it. And so it's also refreshing that they are actually being responsible about referencing others. So the field is taking a much more sober and deliberate path than I think it might have. And I'm very happy about that. And I hope that this type of work will dominate the field, and that will enable it to fulfill its promise. So we don't just have it running out of steam, for example.
I am going to ask about ultimately finding a killer application. But before that happens, before I ask that question, what are some incremental gains or incremental steps of progress that you'd like to see on the neuromorphic photonics roadmap in the next 5, 10, 15 years?
Well, Bhavin, can I start with that? I mean, I think,
yes, please.
I think maybe you've covered some of the challenges already, Bhavin. But I would say that the kinds of, we have the silicon photonic technology, which is great at building linear networks, and we're trying to introduce nonlinearities into it. And there are technological challenges there. Maybe you spoke about this, Bhavin, already, but it would be hybrid integration of other materials, optical memory, key challenges in control processing. You mentioned bringing CMOS on because, we have all this functionality on the chip, but we need to control it as well. But what I would love to see happen, and some people are working on this, is a focus in the near future on not the continuous valued neural networks that we're currently studying on silicon, but the spiking neurons. And that's where I think that there's the greatest potential, because the brain does spiking and it's very efficient at information processing. And we know that spike encoding is the most efficient way of encoding data in a communication system. So the potential is there in building neural networks that use spiking neurons to get the greatest information throughput in the network. And in order to do that, we no longer can have lasers off the silicon chip, laser light coming in and then processing on the chip. We now have to have these spiking neurons themselves integrated within the area of the chip, if you will. So the spiking neurons, the spiking lasers are the neurons. And so a great challenge will be introducing excitable lasers, which are going to involve 3-5 materials within the fabric of the chip, so that we can now network together spiking laser neurons to form a neural network. That, I think, in the next 5, 10, 15 years would be an exciting development.
I completely agree with Paul about this, about the integration of light sources, and also I think in parallel, Paul mentioned this as well about the integration of memory with processes. This is something that is still a huge challenge. It's a big bottleneck. The challenge there is that electronic memories are out there, but when you're in the optical domain and trying to go into the electronic domain, especially when this memory is stored in the digital domain, you need to go through the optical analog to digital electronic, and then when you go back, you need to go from the digital electronic back to the optical analog. So you have this data converters in between that can limit how fast you can get in and out, and also they can be very power hungry. So this is why there's been a big push towards trying to do co-integrated memories with your processes, and that's an active area of investigation. People are using things like phase change materials for implementing non-volatile and also other type of volatile approaches. So, this not only for neuromorphic photonics, but I think for any type of processes in general, this laser sources and memories are sort of the two big challenges to overcome.
So I have it in mind that I wanted to ask about a killer application, right? Everyone wants a killer application, but maybe a better question is, what's the right way to gauge progress in neuromorphic photonics? How is that going to be measured?
Bhavin, why don't you take that one too?
Yeah, so I mean, you're right that so it's always nice to have a killer application. When we see that in quantum computing, right? They always say, if you're able to solve, do prime number factoring, or if you're able to do some quantum simulations, then that would kind of be the killer application. But that still is a long-term metric, and also in neuromorphic photonics, I would say that a killer application that we can talk about, or killer applications, it might not be the best near-term metric. So I think this kind of relates to everything that we've just said right now. I mean, about with in regard to the progress of the technology. So I would say sort of the near-term win points are when we can do sort of on a bit on a larger scale, on a foundry scale, material integration. We can have, as we have also talked about, like integration of memories, integration of electronics. These are all kind of like little checkpoints, right, along the way. I would also say that they are these applications where, and Paul mentioned this a bit earlier, about edge-based type of applications. So it's not necessarily, it might not necessarily be a killer application, but what we have seen is that when photonics is used at the edge based, for example, in autonomous vehicles, in RF processing, it can greatly improve the overall latency, the throughput, and also the power consumption than if you're just using a purely electronic or a software-based neural network, right? So you can kind of, it's not that the neuromorphic photonics provides the best the best precision or the best accuracy, but it does a lot of that workhorse in the beginning, so that it reduces the constraints, so as to speak, on the electronics that comes after it, right? So I think if we can kind of show that, even in the next few years, for RF applications, for autonomous vehicles, and other edge-based applications, and also in optical communications, we talked about compensating for fiber nonlinearities on fiber transmission systems. Again, so I think those immediate applications where you can immediately show this type of advantage in so-called swap, then to me those would be great checkpoints along the way.
I guess I wanted to add that, if I may,
Yeah.
that I think we want to be careful about using the killer application as a metric for what we're doing. I mean, I do think that we need to show what we're doing has application and is going to be useful. But as we've said throughout this conversation, if we were to compete head on with digital electronics for computing or even for signal processing, that's a losing proposition. And we also don't want to be, a solution looking for a problem. That's a losing proposition as well. But I think if we keep in mind that neuromorphic photonics, by its own definition, is borrowing from the way the brain works in some way that we think the brain is doing things efficiently, I think we can use that to guide us toward problems that currently can't be solved. And again, bringing it back to the cyber-physical, at the edge of the system is a place where there's currently an issue. There may be other things. After all, the brain isn't good at digital computing, right? So we need to be sure we're not, comparing apples to oranges.
Yeah.
Well, Bhavin, sorry, go ahead, Bhavin.
Oh no, I would just say that I would add. I mean, just if I was to actually think about a killer application sort of in the future, then I would say that that photonic information processing or neuromorphic photonics for solving what are called NP-hard problems. So these are problems that you cannot find solutions in polynomial time. They're extremely hard problems to solve. These are open, these are some very open-ended questions, and there has been a lot of work in photonics in trying to solve this type of very hard optimization problems. And if you can do this, then I think that would be the killer application. It would have applications in new drug discoveries. It would have applications in any type of wherever you need optimization, to solve optimization problems. So it's I think the potential would be enormous, and the future looks bright.
Well, Bhavin and Paul, I want to thank you both for taking the time to inform our listeners of what neuromorphic photonics is, and then also some insights on the current and future of the technology. I appreciate your time.
Thank you, Jake. It's been a pleasure.
Thank you. It's been a pleasure too.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.